We've been given the equation of a quadratic function s of t, where t is the number of seconds that have passed, and s of t gives the position of a particle in meters. We've been asked to estimate the instantaneous velocity at t equals 3 seconds. I'm going to have Desmos help me calculating values in order to help us get this estimation. In Desmos, I've defined the function as s of x instead of s of t because Desmos doesn't like t as an input variable, it likes x. I've been asked to consider the instantaneous velocity at t equals 3. So first, let's go ahead and just plot that point. I'm going to evaluate s of 3. We see that it's the point 3, 22 that we're talking about. I'm going to add that point to Desmos with a label. I'm going to change my viewing window to allow me to see that point. I'm going to go from an x of -5 up to an x of 6. And I'm going to have my y values go from -5 up to 30. That will allow me to see that height of 22. And then we have that point labeled as 3, 22. The instantaneous velocity of this distance function, this position function, will be the instantaneous rate of change at x equals 3. It'll be the slope of the tangent line at x equals 3. To do this, we're going to use the slope of secant lines from x equals 3 to a point very, very close to x equals 3. And we'll let those 2 points get closer and closer and closer together so that we can estimate the slope right at that point, right at that instant. For example, the average rate of change from x equals 3 to x equals 3.1 is 16.3. The slope of the secant line from 3 to 3.1 is 16.3. If we let the 2 points get even closer together, so now the distance between them is only 0.01 units. I'm traveling from x equals 3 to x equals 3.01, and the change in y over change in x, the slope of that secant line is 16.03. Let's get even closer. When I find the slope of the secant line from x equals 3 to x equals 3.001, we see that the slope of that secant line is 16.03. The average rate of change from 3 to 3.001 is 16.003. It seems to me that as the 2 points get closer and closer together, the slope of the secant line is approaching 16. Let's do it from the other side. You notice that I'm approaching x equals 3 from points that are on the right side of x equals 3, like 3.1, 3.01, 3.001. What happens if we approach x equals 3 from the left side? For example, what if I look at the slope of the secant line from x equals 2.9 to x equals 3? We see that we get an average rate of change, a slope of the secant line, of 15.7. And if we get even closer to x equals 3 from the left side, we find the slope of the secant line from x equals 2.99 to x equals 3. We see that the slope of the secant line is 15.97. And if we get even closer from the left side, we look at the slope of the secant line from x equals 2.999 to x equals 3. We see that that slope is 15.997. Again, these values are approaching an instantaneous rate of change of 16. So as I get closer and closer to the point x equals 3, the slope of the function, the average rate of change of the function, is approaching 16. So I would estimate that at x equals 3, the instantaneous rate of change of this function is 16. I would estimate the slope of the tangent line at x equals 3 is 16.